plants generate electricity for commercial and residential use across the country. To generate electricity, power plants use a typical Rankine cycle with steam as the working fluid. In this cycle, typically a wet cooling tower is used to condense steam. To reduce freshwater consumption in arid climates, power plants can use air-cooled condensers, or ACCs, as their cooling technology. However, ACC systems are highly inefficient during peak power demand due to poor airside heat transfer properties. This inefficiency limits the cooling capacity and ultimately the total power generation. Due to this loss of efficiency, ACT developed a high thermal performance supplemental thermal storage system that reduces dependency on water cooling for electricity generation. ACT's supplemental thermal storage system for power plant dry cooling uses no fresh water while providing similar cooling performance to wet cooling towers. The supplemental system takes advantage of cooler ambient temperatures found at night and stores waste heat in a phase change material reservoir during the day. By doing this, the power plant is able to have a cold sink available during peak demand when the ambient temperature is typically the hottest. Through utilization of a high thermal performance loop thermosiphon, the system transports heat to the PCM reservoir and ultimately rejects this heat to air. Phase change materials, materials that melt and freeze to store heat in the latent heat of fusion, are used to generate this cool storage. During the day, the loop thermosiphon transfers waste heat from the power plant steam cycle to the phase change material, which causes the phase change material to melt. At night, another loop thermosiphon removes heat from the PCM, solidifying it while transferring the heat to an air-cooled radiator. At ACT, we designed and fabricated a prototype system that can store over 30 megajoules of thermal energy. A steam evaporator mimics the Rankine cycle to store heat in the PCM reservoir, while a typical air-cooled radiator removes heat, both via the loop thermosiphon system. The prototype, at optimized boundary conditions, melts in 11.5 hours. This experimental result matches within 10% of the finite element analysis modeling results. When the accumulated energy curve matches the latent heat capacity of the PCM, then the PCM is considered fully melted. The subsequent graph depicts the trend in power, refrigerant temperature, and PCM temperature during cycling. The refrigerant is the heat transfer fluid used in the loop thermosiphon to transfer heat in and out of the PCM heat exchanger. This thermal cycling can be repeated for long-term use. The result is a system with comparable thermal performance to wet cooling towers and no water consumption. The system uses a low-cost salt hydrate PCM reservoir and conventional engineering materials for manufacturing for additional cost savings. The advantage of salt hydrate PCM is the low cost compared to paraffin waxes with comparable latent heat capacity.